Hi guys, I hope you are doing good. Okay, so in the previous two lecture, we have learned this component of the computer system and the introduction about the assembly language, assembler, linker, and these things. So today we are again, it's a part of the introductory course, like what exactly why we need the my memory hierarchy. Okay, there are the memory hierarchy in our system, but again, guys, I'm going to request you, please subscribe my channel, please share the video if you like the content. And soon I'm going to using the whiteboard as well for your clearance. Whatever we are going to study, we will see with the example. I'm also thinking to post the lecture related to machine learning. So guys, these videos is gonna be very helpful for you. So I'm going to request, please subscribe the channel, please share with your friends, and if video looks good, then please tell me in the comment. Okay, okay guys, in this lecture we are going to study the memory hierarchy and why we need the memory hierarchy. Okay, from here we can see like the widening speed gap. As you know, like there is processor. Okay, there is processor, and here it is memory. Okay, here it is memory. So between the processor and the memory, there is the buses. Definitely, whatever we are going to access the data, we are going through the address bus. We are going to access through the data bus. So it's a very wide gap. Okay. So the definitely speed is less as it's showing. Processor operation take less than 1 nanosecond. Why? Because it is in the processor. Okay, within the processor, whatever is going to be, it took only 1 nanosecond. It's okay, but main memory requires more than 50 nanosecond to access. Mean when, let's suppose I need some data, so our address bus will be load the address, and we will load the data on database, and it will come toward our processor for the fetching. It will send the so it will take the 50 nanosecond. Just consider 15 nanosecond. It's a big time. So this gap is going to be increased, so that's why we need some hierarchy maybe. So that's why the widening is increasing. Okay, so here each instruction involves at least one memory access. Whenever each instruction, definitely it access the memory, huh? So a second memory access for load and store instruction. While we need the memory data, definitely we are going to access the memory location. We load to address, then the these from that location we are going to fetch the data, and we are going to take the data. So this he is telling here at the process. Okay, so memory bandwidth limits the instruction execution rate. So we know the memory bandwidth is also limited. Okay, again the cache memory can help bridge. Here actually the cache memory came. Okay, cache memory, what is the cache memory, we are gonna see. Okay, cache memory is small but in size but fast. Why it is fast? Because it is in the processor. It is in the processor, it is not outside the process, it is inside the processor. So this is actually the hierarchy. Okay, this is like hierarchy in the processor. Okay, it starts from the register. As we know, registers, general purpose registers, it could be like 8-bit or 16-bit. So we can store like 2 raised power 8 or 2 raised power 16 value. If there is like this type of data, okay, we can use the register, and the register is more fast than the cache, and cache is more fast than the main memory. So if initially we get our data to the register, if not, then it is in L1. There is an level 1 cache, then we have level 2 cache. Okay, and these three things are inside the processor. Okay, then from the processor to the main memory, there is the bus. Okay, memory bus. So here it is the memory bus we use to access the memory. Okay, whatever we have load in the memory, and then the memory is connected with the disk and tape. Okay, so first of all, let's suppose I am going to read anything from the system. What the processor is do? Processor will see for that data. Is that data is in the register? If it is okay, good, very good. Our this will hit, and we will get our data very fast. If it is not, this will then it will be checked in level 1 cache. If it's present, good. If it's not, then it is checked in level 2 cache. So this system is taking very few nanoseconds. Okay, we will see here. So because it's in the processor, and if it's not into the level cache, then the on the memory address we will put that address and we will go to our memory, and we will see if it is in present in the memory, good. And if it's not, then we will see in our other hard disk or tape or whatever it is. Okay, so if it is like register at the top of the hierarchy, and it mostly is like 1 kb. Okay, mostly like size in it's less in size. Okay, but their access time is very very fast, which is even less than zero point 0.5 nanosecond, guys. Okay, and about the level 1 cache, it could be like 8 to 64 kb. Okay, 8 to 64 kb. Again, in computer architecture, kb, kilobyte is 2 raised power 10. Okay, megabyte is 2 raised power 20, and the gigabyte is 2 raised power 30. Okay, so level 1 cache could be like from 8 to 64 kb. Okay, it is also very less in size, but the access time is from zero point 0.5 nanosecond to 1 nanosecond. Okay, then level 2 cache, it is little bit higher in size, which is 64 kb to 8 megabyte. Okay, but the access time is little bit higher, which is 2 to 10 nanosecond. As we are going down, the access time is gonna be increased. Okay, because size is going to be increased, definitely then access time is going to be increased. Okay, so when we came to the memory, up till now we know we have like 64 gigabyte, and we are thinking like for the more, but here the time is 50 to 70 nanosecond. Okay, for the one cycle, for the one fetch, complete load and store cycle, it took like 70 nanosecond. Okay, and then disk storage, it's like 200 gigabyte, but up till now it's like teras. It's in the teras. Okay, so in teras it's like milliseconds. Okay, so that's why we need hierarchy. When we need fast access data, definitely we will, and it's small data, we will use the register. And if it's like little bit big data and we need even the fast access, we will use these cache. And we need the huge data to access, then definitely we need the memory, but it will take little bit, 50 to 70 nanosecond. Okay, so that's why we need the memory hierarchy. And again, here the processor came, as I told you in first slide, like in the processor we have two things: the data path and the control unit. Okay, the data path is nothing, it's actually the part of the processor that execute the instruction. Okay, whatever the instruction is, what is next instruction is going to be fetched. Okay, this is from the data path. And the control is nothing, it's actually the signals. Okay, it's generate the control signal for each instruction. Okay, if we will see here, let's suppose this is my instruction cache. Okay, instruction cache have nothing but it has the instructions. Okay, what is the program counter or the PC? Program counter tells the system which next instruction is going to be fetched. Okay, which next instruction from the instruction cache, there are some instructions like this. And so which next instruction is going to be fetched, it's tell by the program counter. Okay, so we can see in the red, these all are the control signals. Okay, in the red, these all are the control signal. So this control signal actually tells the processor, okay, at this time, which process is gonna be done. Okay, if this process, if this is one, okay, we will say, okay, this from the register we are going to, whatever the operation is going here, we will do the register operation. And if this is one, okay, we will say the processor will know, okay, this ALU operation is gonna be done. Okay, so this is the control, which actually generate the control signals. And the other one is the data path. Okay, so data path is what exactly it is, we will see deeply in the next lectures. Okay, data cache have the data, ALU, the arithmetic logical unit, which actually do this addition, subtraction, multiplication, and this stuff. Okay, I hope this is clear. And now the data path component. This mostly question came in the exam. Write the data path components. Okay, so there are like program counter. We see like the program counter, which actually contain the address of the next instruction, which is going to be fetched. Okay, and the next program counter is actually compute the address of next instruction by just incrementing in the address. Okay, so we have instruction register, which stores the fetch instruction. Okay, which instruction is going to be fetched, it store actually the instruction register. Then we have instruction and data caches, small and fast memory containing most recent instruction and data. Okay, whatever the recent instruction is fetched, it is stored in the instruction cache. Okay, then the register file, these are the general purpose register. It can store 8-bit or the 16-bit data. Okay, these are for the general purpose. ALU, addition, subtraction, multiplication, Buses, again the same thing. Load used to write and interconnect the various component. Okay, let's suppose memory with the processor, memory with a register with the processor, so it interconnects actually. Okay. Okay, so here the fetch cycle came actually. Okay, we have the whole execute cycle is this one. So it start from the fetch. Okay, this is like if instruction fetch. First is instruction fetch, then id. And please guys, you have to remember it is like it is in the same manner. Okay, because this is happen in the same manner in our system. First your instruction is fetched. Okay, then your instruction is decoded in the system, then your instruction is execute. Okay, based on what the instruction was, because in decode we will see what is instruction. Is it add, is it subtract? If it's add, subtract and ALU instruction, then definitely it will toward the ALU, and then the execute the command. Then in the execution of the command, definitely we are going to access the memory. Maybe we are going to store, maybe we are going to load. So we'll access the memory and then write back mean whatever we did the operation, definitely we have to write back the data in the memory. Okay, so this is the cycle. In the same way you have to remember. Okay, instruction fetch, instruction decode, execute, memory access, and write back. Again in fetch you will study here like the fetch instruction compute address of next instruction. Decode actually, as I told you, let's suppose I have an instruction here. Let's suppose I have an instruction here, add a comma b. Let's suppose I have this instruction here, it is decoded. Okay, this he will see. Okay, from this opcode, from he will see from this opcode, because here it add, so it will say, it will tell this system like okay, it's add, it's ALU operation, and here it's the operand, so the this will execute in ALU. Okay, it will compute the result value. Then definitely maybe A or B, as I told you, A could be the register, B could be the register, A and B could be the memory addresses. So definitely we are going to access the memory, and then we are going to write back the result, and then again this cycle is going to be start for the next instruction. Okay, and next come the like technology improvements. Okay, oh, initially vacuum tube was used, then transistor came to store a bit. Now the IC came, and these days very large scale integrated circuits are used. Processor, as we know, like transistor count, initially there was very less transistor, but now nowadays there are the Moore's law, which say your capacitor size is going to be increased, with I think so 2% or 20%. This is a Moore's law. But definitely the time will come where our chip will not will not accommodate the more transistors. Okay, so that's why people are thinking about another ways for the storing the bits. So up till now mostly people are considering the transistor, but in coming days definitely the new systems are coming. Okay, that will not consist on the transistors. Again, the memory DRAM capacity about 60% per year, increasing 60%, four time every 3 years. Okay, and the cost per bit, definitely cost is gonna be decreased. Okay, and this capacity, initially it was like some kilobytes, then megabyte, now it's in the gigabytes, terabytes. Okay, so these are the as technologies are going to be advanced. Okay, we can see here in 2008 here, the DRAM is 1 gigabyte, but up till now in 2013 it is like 64 gigabyte. Okay, in 2013, I think the 2013 or 2018, up till now 2023 it's like 64 gigabyte we have. Okay, so here you can see the performance of the processor with the time. Okay guys, I hope this up till now you guys are very clear about this. And then we will start in our next lecture, we will start about the data representation, how data is represented in our system, how our system actually know the data in which format. We will see all the formats. Okay, so I hope guys you are very clear up till now. And again at the end I'm going to request, please subscribe this channel, share this video with your friends, so that, and please press the bell icon, so whenever I'm going to load the video you guys get the notification. And if you have anything, please tell me in the comment, and soon I'm going to upload the another video for the other topics as well. Thank you guys.